Hello everyone. Today I'm gonna talk about CLIP, a paper recently published by Openai. CLIP stands for Contrastive Language Image Pre-training. As you see here, CLIP, the name is different from the topic of the paper. In my presentation, I will go through some uh, parts and explain what can CLIP do. How does CLIP work, and I will try to explain the clip model in depth, and at the end I will go through an example and working with their model, the code, which is a free access, and explain the model better. Experiments done with clip. They did some experiments, did classification with different data sets available, and compared their model with some available state-of-the-art models. Limitations, and talk about some uh, limitations that uh, this model had, and at the end we'll go through the applications and talk about some applications available in GitHub. First, what can Clip do? Clip can tell if an image and a short piece of text belong together or not. As you may know, Dolly can produce an image for us when we read a text to the model, but Clip is not like Dolly. It means that we cannot give an image to the model and expect the model to produce a text for us, or give a text to the model and produce an image. Just the model can say whether a short piece of text is related to an image, belong to an image or not. For example, here we have an image, a great view, nice view. A car parked on the beach at sunset. If we if this to the model will say that they are related, they are together. But uh, why do we need to find the correlation between text and image? What is the advantage of this? There will be some consequences. We can use it for example, for image recognition. For example, Clip can do classification. Here we can see an image, and Clip did a classification. Uh, Very good, and there will be some other uh, usage of this model, and we will go through it at the end when we are gonna talk about the applications. How does Clip work? This is the figure I picked from the paper, and I'm gonna talk about the model in this part. The novelty of the paper was the data set that they generated. They use internet and social media like Instagram to produce 400 million pairs of image and text, and they train their model with that data set. Here we can see that here is a batch of text and images. They are corresponded to each other. For example, this the first image and the first uh, description, the text file, and you have they use text encoder and image encoder. For the text encoder, they use that transformer explained in the paper, in the publication named attention is all you need, but they use the modified version of that. For the image encoder, they use two different models. First, ResNet, but again they use the modified version of ResNet, and they did some replacement. For example, instead of using global average pooling, they use self-attention pooling mechanism. And the other model they had was VIT, but with minor modifications. For example, adding a normalization layer, and also using use different initialization scheme in the VIT model as the image encoder. Here, the text after embedding, they feed it to the text encoder, and at the end they did a linear projection to produce these presentations of the text. And n here is the number of samples in the batch. And here, after doing some augmentations here, and regarding the augmentations, I should mention that they didn't um, use augmentation like playing with the resolution or flipping the image. They did some just cropping and preparing the changing the size of the images as what the model expect. For example, VIT expect the image size to be 224, so they did center cropping to keep the uh, as much as information they can from the image, center cropping, and then changing the size of that to be 224, and then feed that to the model. And at the end, again, with linear projection, they generated the representation of the images. And here again, n is the number of samples in the batch. And at the end, they created these metrics named similarity metrics. The elements of these metrics is the dot product of these representation of the images and the representation of the text. For example, here I1, T1, then I1, T2. And the objective was that in increasing the value of these elements on the main diagonal to be 1 and pushing the other elements to be 0, because we know that I1 corresponds to T1, so this value must be higher than the other values in this row and in this column. This is they did the cosine similarity with the with doing the dot product. I will explain it in the uh, next slide. The method was not new. It was used in the other paper they cited. In that paper, they used this model for medical purposes. Here we have the medical images and the corresponding texts here. They did some augmentation, but again, the augmentation in clip was as cropping, and then feeding the images to the image encoder, and at the end do some non-linear projection to have the output, to generate the output. But in clip they didn't use non-linear projection, they did linear projections. Here the non-linear projection could be MLP or like that. Regarding the text and some augmentation, and then feed it to the text encoder, and again doing nonlinear projections. But again, in clip it was not nonlinear. They did linear projections. The loss functions here are the here we have the cosine similarity, the dot product, and then exponential, and over the summation of exponential over uh, the elements. Let me explain it on the clip model. Here we have the cosine similarity, the dot product, the exponential over the summation of exponential. This is the softmax. We already know that, and at the end minus log would be create the cross entropy. So their model was uh, a straightforward classification model. Here, this is the loss function over row. This is loss function. The other one is loss function over the columns. Here, for example, for this element, we have the loss function here over row, then the cross entropy over the column for this over row or column, and at the end, sum them up here and use this lambda, which is a hyperparameter, and divided by n, which is the number of samples in the batch. Here is the overall loss function, which is a weighted average of these two loss functions. So this is just as doing softmax and then cross entropy. And at the end, with this loss function and doing backpropagation, they try to decrease the loss function in some method. Here, the second part of the model, doing zero shot prediction. Zero shot prediction means that without any further training, feed in the image and do classification. Here, we have a dog and we have 10 classes, 10 possible classes. There are the classes of the C14, I think. And another thing that I should mention here is that they didn't use the labels like playing car dog. They created descriptions like this: a photo of a dog, a photo of a car, and then do embedding and feed it to the text encoder, and then created the script, the presentations here. And this was new in their model. Uh, and with that, you will see that um, they paid more attention to the details of the images. For example, in the next slide, we see an example and go through that. Here we feed the image to the image encoder, and then at the end do the dot product and the softmax and check which one of these values is higher than the others, and we can see that the image is corresponding to the third class, which is a dog. Here we can see that we have three description: a photo of a bird, an image of a bird, a photo of a bird sitting near bird feeder. All of them are explaining this image, and all of them are true, but the third one gives us more information about the image. Here the bird feeder, the bird sitting near it, and if we do the dot product using the clip model, we can see that the value corresponded to the third description is higher, and the image is or this class. So the clip model pay attention to the details of the images, very uh, good, and they didn't use a label like this, a bird or a dog. They created some descriptions. Experiments done with clip. For example, here we zero shot clip is competitive with a fully supervised baseline. Here we have we are comparing. They did comparing the model, the zero shot clip, again without any training. Did a classification over the different data sets and compare it to the ResNet 50, but with linear prop. What is linear prop? Um, uh, for example, the ResNet is trained on ImageNet and have layers, several layers. Keep train the model and keep all the layers with the exception of the last layer that is for the classification. And keep all the layers with the exception of the last layer, and add another layer at the end of that for the linear as a linear prop, and do the training and do the classification over the on the different data sets. This is the linear prop. And here we can see that zero shot outperformed ResNet 50 over different datasets, and this is very interesting that ImageNet, the ResNet was trained on ImageNet, but zero shot is doing better in this dataset. But we can see that some datasets in the other datasets ResNet do better. Zero shot clip outperforms few shot linear props. Again, linear props means that we keep the model, just remove the last layer and add a linear prop at the end of the model but after training. Add a linear prop at the end of the model, and then train the model and then do the classification. Here the zero shot is better than we have three popular models here. Zero shot is better than them, although they had training. For example, here they had 16 training examples per classes, but the zero shot was better than them. But for the clip model, if they use the linear prop, the same as them, at first we can see that the performance of that was uh, was not good at the first steps because the weight was changed, and then uh, they updated. But after 8 or 16, we can see that the performance was much higher compared to the other different models. Zero shot clip is much more robust to distribution shift than standard ImageNet models. Here we can see that the ResNet the accuracy is decreasing when we are going from this dataset to these dataset that are much harder to be classified. But zero shot clip is doing great on all of them. The reason is that with a great chance the clip models saw these images before, and some of these images maybe might be in the data set, might be available in the data set, and zero shot saw them, so it's doing good on the uh, data set. For example, the ImageNet sketch, and 24 25 compared to 60% the accuracy. Talk about the limitations. As we saw before, the image the clip model is not good on or is not didn't do good over all the data sets. If we want to have a state of the art clip model, we need to increase the computation by 1,000 times, which is kind of impossible. Clip is not good for all tags. Here we know, or you might be familiar with the MNIST dataset. Is an easy dataset. They got just 88% accuracy on that easy dataset. The reason was that they handwritten and there were a few handwritten digits in the dataset, so the clip didn't see them very well, didn't learn them very well. And clip is not a caption generator. At first I mentioned that, and we cannot feed an image to clip and expect clip to generate the image for us. Applications, image search engine. Vladimir, and I found it from the GitHub. Use clip to generate images and two dogs playing in the snow, or the word love written on the wall, and then use it as a image search engine. And then another team use it for object recognition, for counting, for color recognition, and we can see that here, the doing probabilities to these two uh, descriptions. And here, if we mm, they mention that if we give a short piece of text, for example, a happy potato, top 9 matching images come to the picture. And here we are done. Thank you so much for watching the presentation. In the next step, I'm gonna go through an example and explain the clip model a little bit more. Thank you. Hello again. Here I'm gonna talk about go through an example and do classification over some images with clip. Here they mentioned that we need GPU runtime. I said it already. Here we download the dataset, download the clip model. It's done, and import the packages, import the libraries need. And here import we want to see the clip models. As I mentioned in the slides, they use two different models: ResNet based models and VIT based models. Here they imported the VIT model, and you want to use it for the image encoder. Here we can see the features of this model. The model parameters about 150 million parameters, input resolution 224. As I mentioned in the slides, they do when they want to do augmentation on the or the images, they do cropping, center cropping, and they resize the uh, images as the and change the size of the images to what the model expect, which is 224 here, and the context length 77. When you want to tokenize the text descriptions, it needs to be 77, the size of the tokens, and then to be fed to the text encoder, and the vocab size is about 50,000. Image processing. Here, image processing, you can see that they did resizing, changed the size of the images to 224, and then normalization. Here we can see that for creating the tokens, the tokenized hello world as an example. Here we can see the size of this vector must be 77. Let's see. Then you can see that yes, it's 77 as the model expects. Here we have 8 uh, example, and in this dictionary they created the description of each image, and the images are here. They're plotted. We have 8 image here, and they don't use just a label for that. For example, here an astronaut, or a bracket, a coffee, a cup or a coffee. They use a description, a cup of coffee. And building features. They do they're stacking the images together and creating the and the, tokenize the tokenize the descriptions. Here, let me. It's good to see the image. What is that image input? That shape. It's good to check the shape. Uh, we have 8 image here. Is 3 RGB. Is different from cross, and the number of channels comes first. 224 by 224. And if we check the print text tokens, text tokens dot shape, it's a 870 by 7 because we have 8 images, 8 descriptions, and each description uh, seven each vector has a size 77, and they are generating the image feature and text features by feeding them to the text encoder and image encoder. Let me uh, check the image features. Image features dot shape. Here we can see that 8 512. 512 is the size in the transformer that, and then we have 8 representations of each image, and each vector has a size 512, and the size of the text features also must be the same, because we want to do the here am I right, yeah, we want to do the dot product between these 8 vectors, so they must be the same, the size must be the same, and they are the same, 512. And here they are creating the similarity matrix. Let me again print similarity. Where is that similarity? That shape 8 by 8. We have 8 feature, 8 text, and 8 images, 8 by 8. And here they are plotting this similarity, and here we see the main diagonal. And at the end, they want to do zero-shot image classification. They want to see classify these 8 images with C for 100 and see find the uh, corresponding class between these 100 available classes. And here they are creating the the descriptions based on the labels of the classes in the C for 100. Let me here check that text description. Let me print the uh, this is these are the classes available in the C for 100: apple, baby, bee, boy, rich, boss, or 100. And when let me see, print. Here they created descriptions based on the labels, based on the labels, and add this description before the label. Let's see what are they look like. Text descriptions. Yes, printed. Here we have apple, but when we add it to before that, this is a photo of apple. We talked about the use this description and tokenize them before feeding them to the text encoder, not just the label. just a word. Here, this is the text feature, and at the end, do the classification. The text features. Here, let's check the print text features dot shape. This is the shape of. Let me paint. Show you here. We have um, we have 8 images. Here we have 8 images. We want to classify them based on C400. So the 8 representations, not the images, after the output of the transformer, the image encoder. And here we have 100 representations of the 100 classes available in DC 400, 100 of them. And each of them have the same size. As you see here, the size is 512. 512. And the size of the each representation of the images has the same size, 512. So we can do the dot product and create the um, similarity matrix, which is 8 by 100. See, and then do the softmax for each row and find the highest value in each row to see each image correspond to which of these 100 classes. This is what they did, and here they plotted. And here, if you check it here, they want to mm, generate five highest values in the in each row. Their softmax, five highest values. So after printing, for example, here we can see that little camel plane, and for this is a text. I think it's wrong. I don't know. It's the racket. It's a cup. It's a man, and so on. But here, let's see if there is a cat, because it's sweet pepper. If there is, let's see if there is a cat in the C400 or not. Can check it. Okay, good. Mm, print. For example, cat, because it's in small. Okay, cat in uh, this C400 classes or not. No, it's not. There is no cat. And also for this image, it's horse. But let's check if there is a horse in the horse. Check. No, no, there is no horse. But this is the uh most similar, class in the C400 to this horse, this cattle. And we are done. Thank you so much again for watching this presentation, and bye.